So you are at a base on the moon when you get the phone call from back home on Earth saying there's been a disaster and no new supplies will be arriving anymore. What do you do? Today we are going to be discussing life support, how we keep people alive in places we didn't evolve to survive in. Space is a pitiless place that is full of stuff that will kill us, and devoid of the stuff we need to live. Science fiction makes a lot of mistakes about what can kill you in space, how quickly it can do it, and how hard or easy a given risk is to deal with. But it tends to get the overall concept correct. Space will kill you. To survive in space, we need to consider everything a person needs to live, and we can rank those in order of urgency. But there are two we will skip, which are also the most important resources in any survival situation, which is knowledge and the will to survive. The former seems kind of obvious, and the latter a bit jingoistic, but there is a reason why just about every manual and guide on survival stick these in bold and repeat them over and over again. During an immediate life and death situation, our reflexive urge to survive does just fine, and it's knowledge and practice using it that tends to fail us. People stumble around, not sure what to do. But in extended circumstances, it is often that desire to live that gets degraded. We've all seen that happen to folks, and while it's a bit sugary sweet to say a good pep talk and a hot bowl of chicken noodle soup will magically fix everything, the psychological aspect of survival is very real. If folks give up, the game is over, and they often do so before they've exhausted all the options, even if they think they have. It's also infectious, causing those around you to give up too, even if they might have seen a solution you missed. Never give up, never surrender is not just a jingo, because while you are still looking for solutions, there is at least a chance you might find one. There is a myth that goes around that astronauts used to be given suicide pills in case they were faced with a hopeless situation. It is a myth, by the way. Something like that would be quite counterproductive due to its demoralizing effect. Also, somewhat redundant anyway. It is by definition usually very easy to get yourself dead in life and death situations, so packing specialized equipment for that contingency seems kind of superfluous. Not the best approach when you are running out of air either, since a corpse doesn't suddenly become a chemically inert piece of furniture no longer consuming or emitting gases. Many of those are quite toxic, or at least distracting, in an unventilated space. This of course brings up our first and most urgent life support concern, which is air. During the course of a day, a person will inhale oxygen and exhale about 1 kilogram of carbon dioxide. Carbon dioxide being molecular oxygen plus a carbon atom, if you are exhaling 1 kilogram of it, you used up about 730 grams of oxygen doing so. The amount you need of course varies by person and what activities they are up to, but this is mostly about how many calories you are burning. There's another myth that you shouldn't be doing much talking when there's limited air because it will use it up even faster, and it is technically true since speaking does burn more calories than not speaking, but the difference is minimal. As a rule, what raises your heart rate uses more oxygen and vice versa. Running out of oxygen is generally not the immediate problem where air is concerned either, it's the carbon dioxide filling up the volume. Let's assume for the moment I am in a room 2.5 meters high by 8 by 5, or 8 feet high and 26 by 16 feet wide, for an even volume of 100 cubic meters. A cubic meter being 1,000 liters, it has 100,000 liters of volume. Volume and mass are not the same thing, so for instance oxygen takes up 21% of that volume, 21,000 liters, but is 23% of the mass, most of the rest being nitrogen, which is lighter than oxygen. The density of air varies a lot with temperature and altitude, but at room temperature is about 1.2 kilograms a cubic meter. So our room holds 120 kilograms of air, and 23% of that is oxygen, 28 kilograms, or 38 days of oxygen for a person. Incidentally, you will often see this figure given as about 550 liters of oxygen per day instead, but 38 times 550 is about 21,000, and as I mentioned a moment ago, that's how much oxygen there was by volume. You can get yourself tripped up sometimes though when people are talking about percentages by mass and by volume. Now you will not survive for 38 days in that room, even if you could get rid of the carbon dioxide that will start poisoning you pretty soon. Because once that oxygen gets down to about half that concentration, you will have problems breathing it, and various side effects will kick in, making you nauseous, lethargic, unconscious, and eventually dead. If you could shrink that room, it would help extend your life. The air is mostly nitrogen, so it would get harder to compress, and eventually that nitrogen would get concentrated enough to cause issues too. Of course, humans don't need nitrogen, and can survive at a lower pressure with just oxygen, so we often only partially pressurize spacesuits because all spacesuits leak, and everything leaks slower at lower pressure. Before we get to carbon dioxide, we should talk about two common science fiction myths in this regard: how long before the air runs out, and how fast air gets sucked out through a hole. Let me dispose of the second one first. If you poke a hole in the side of a spaceship about the size of your finger, about a square centimeter, you will lose about a kilogram of air a minute. If you stuck your thumb over that, you would plug that leak, and it would not rip your thumb off, let alone drag you through the hole like a sausage grinder. The air loss will slow as pressure drops, but you won't pass out till it gets at least under half an atmosphere, and in that 100 cubic meter room we just discussed, that would take an hour. It's also very easy to find leaks, especially in zero gravity. Leakage rates loosely go with the area of the leak. Twice the area, twice the leakage. Even if you put your fist through the hole, you should have a few minutes to do something about it, and random objects flying into the hole would help to partially plug it too. That's the major reason we use partial pressure in spacesuits, and use only oxygen, not nitrogen. Again, all spacesuits leak a little bit, typically through the joints, and lowering the pressure in them slows that a lot, particularly since those tend to be the kind of leaks that get bigger when they are pushed at by more pressure, further increasing the leakage rate higher pressure causes. In regard to the first of the two myths, running out of air, the air supplies in an Apollo-era space capsule were pretty tight, because there wasn't much space, so it gave rise to some bad ideas. Your typical science fiction spaceship tends to be a lot roomier. Nevertheless, when power runs out or life support fails, the crew often seems on the ragged edge of death in hours or even mere moments. This is just wrong. Someone once made a nice table of volumes of various famous spaceships in science fiction, and came up with a volume for the USS Enterprise D of just under 6 million cubic meters. That's the one Picard captained, not James T. Kirk. Ignoring any reserves of air they would presumably have, that would be 1,656,000 kilograms of oxygen, or about 2.3 million days worth of supply, 6,200 years for one person. It had a crew of 1,000, so that would be 6.2 years, and at least a couple years before the oxygen deprivation would be an issue if they did nothing. Of course, carbon dioxide gets to be a trickier issue. That can start causing problems even before you get to 1% by mass. 1,000 people will exhale 1,000 kilograms of carbon dioxide a day, so they'd hit 1% carbon dioxide by mass in just 72 days. Again, not really a time-critical problem. Once it hits these concentrations, the side effects will begin to impair your ability to get things done too. Headaches, dizziness, and irritability get common, and don't help you think of solutions to your problems. All of this gets steadily worse as concentrations rise till it eventually kills you somewhere above 10% by mass, about 7% by volume. So it isn't an urgent issue on the classic big capital ship we see in science fiction. Even on the International Space Station, which is not noted for its abundant elbow room, at 900 cubic meters of volume for 6 people, it isn't that urgent. You have about 2 months of oxygen. However, you only have about 2 days before the carbon dioxide would start causing problems, and maybe a week before it got too severe for them to operate. Death would arrive probably inside another week. Obviously, the ISS has ways of scrubbing carbon dioxide from the air, and indeed there are many options available to us, but let's do our hypothetical scenario on a base in Shackleton Crater on the Moon instead, one of the places we often think about constructing such a base. Now, as mentioned, there are tons of ways to get carbon dioxide out of your air. We developed many for space travel and submarines, and we've learned even more in trying to deal with carbon dioxide in our own atmosphere. These typically fall into 2 major types: regenerative and non-regenerative. The latter typically involves some chemical compound that is expended during the process, often using up about an equal mass of that material to the carbon dioxide it removed, which at a kilogram per person per day can mount up pretty fast. Where it is the non-regenerative kind, say calcium oxide or quicklime, you are using that up to remove carbon dioxide, as it absorbs the CO2 and becomes calcium carbonate, the stuff shells are made out of, and is then done. If you begin with, say, 56 kilograms of calcium oxide, you will end with 100 kilograms of calcium carbonate, having absorbed 44 kilograms of carbon dioxide, just 44 days worth for one person. We'd much rather not be left with 100 kilograms of useless calcium carbonate, so we prefer some way to sieve through the air and remove the carbon dioxide, to just dump it out in airlock, or to just turn that carbon dioxide back into oxygen. That's the usual notion behind a regenerative scrubber. It either captures the CO2 in some form you can use or toss out, and which leaves the scrubber material unchanged afterwards, or does one better and produces oxygen again by removing the C from the CO2. Plants, of course, do just that. They suck in carbon dioxide and emit oxygen. We can also eat plants, so it's a great option, but it takes up a lot of space, time, and energy to grow plants. Often the energy to remove carbon dioxide that way is a lot higher than the alternatives too. It's very hard to separate carbon dioxide into oxygen again. It's not the path of least resistance. And the various good techniques for doing that efficiently tend to be a bit on the bulky side. Carbon sequestration, when done at the large scale, can do as good as a couple hundred kilowatt hours per ton of CO2, which would convert into about 720,000 joules per kilogram, or about 8 watts per person. We've also seen some interesting research recently into breaking up with ultraviolet light, and potentially using nanoparticles in tandem with ultraviolet to convert carbon dioxide into oxygen and methane. In any event, that would mean you could convert your CO2 back into oxygen in a spacesuit using a solar panel small enough to comfortably fit on your air tanks, which would be very handy. In an ideal case, a spacesuit would be able to scrub that CO2 indefinitely with a power source, and also extract oxygen from water or even oxides and rocks. As we'll see in a bit, that's not too energy intensive of a process, but trying to get such processes down to the small scale without losing tons of efficiency can be tricky, especially miniaturizing it to the degree necessary for a spacesuit. But it does give us a decent scale for a hypothetical moon base, 8 watts of power generation for CO2 scrubbing per person, under optimal scenarios. Over there in Shackleton Crater, we have the advantage, as we discussed in the Moon-Based Concepts episode, of spots along the rim of the crater that are almost perpetually lit, making solar power a nice option, though fission is also an option. Down in the crater, we believe there to be an abundance of water ice available too, and you can get oxygen out of ice for around 30 million joules a kilogram. The moon is also about half oxygen by mass, even though it is mostly tied up in oxides, but you can pour oxygen out of rock if you need to. The energy needs to do this are pretty high, usually on an order of around 100 million joules per kilogram of oxygen, which would be more like 1000 watts per person, compared to about 10 watts that scrubbing carbon dioxide took per person. So it's a good way to get oxygen to begin with, but it's clearly better to recycle it. It's cheaper to get oxygen out of water, more like 300 watts per person, but water is a lot less common on the moon than rock, and you might want to do other things with it. I keep mentioning these wattages because energy is always your ultimate bottleneck, and a lot of times people just assume using plants for recycling is going to be better. That's only ever true because you can also eat those plants, and you need to grow them anyway if you don't want to starve. Of course, that's not all there is to air. Indeed, air has moisture in it, and regulating humidity can be an issue in keeping good health, especially where plants are concerned. But most of the air is actually nitrogen, and while humans don't use it to breathe, our plants do. That's a serious issue, because plants are always the preferred long-term means of recycling air, since it takes less plants to recycle a person's air than it does to feed them. If you need those plants to eat, you might as well let them do your recycling too. Waste not, want not. There seems to be very little nitrogen on the moon, and Mars not much better. We are not actually sure how little there is, but it certainly is not abundant. Concentrations are low, on an order of a percent of lunar regolith, It's not tricky to bake that out, but it is energy intensive. To a degree that's okay because you can probably get it out as a byproduct of all the smelting you'd have to do to get the construction material to make greenhouse domes there if you decide to grow food. Moving on to water, we'll find this is actually one of our easier issues. In our base in Shackleton Crater, we'd expect to find a lot of ice mixed in with the regolith there, and we can just cart that inside and melt it and filter it. Many places in the outer solar system are super abundant in ice. Unfortunately, in the inner solar system, not only is it rarer, but so is hydrogen. You can find oxygen everywhere, and of course the single biggest concentration of hydrogen is in the inner solar system, but that's in the sun, and getting at that is fairly difficult. If you've got hydrogen and oxygen, you can make water. Unfortunately, most places that don't already have water don't have much hydrogen either, so generally you either have plenty or you have none. Getting it into drinkable format is a bit tricky, as is recycling it. You can of course evaporate water out of any mixture of seawater or mud or human byproducts, but that's quite energy intensive, typically on an order of hundreds of times more so than options like reverse osmosis. But water, the keystone of life, and what most of your body is made of, is actually one of the easier parts of our life support problem. Energy needs generally run on an order of 1000 joules per liter of water treated, though it can be a lot higher depending on circumstances. But if we assumed you needed around 100 liters a day, then this would be a power need of about 1 watt, a lot less than would be needed to heat that water for a shower, for instance. NASA has invested enormous energy into recycling sweat and urine, and has gotten very good at it, less so solid waste, and that usually mostly goes overboard. I have folks frequently ask me about debris in orbit as a hazard, and it is something we will get to in the not too distant future in an episode with the working title of Space Trash. But yes, there is a lot of shit in orbit, and yes, a lot of it is literally that. Needless to say, you'd want to recycle that too if you were planning on agriculture on your moon base. It's actually a bit harder in space as opposed to on the moon. There's less gravity there than on Earth, but there is some. And so on the ISS, we actually have a keg that spins around to provide centrifugal force to simulate gravity, to help remove contaminants from water when we're filtering it. Gravity, even in small amounts, helps to ensure dust and water settle out of the air and make sure a lot of biological mechanisms function properly. We do not know the real long-term effects of low gravity, or even zero gravity, all that well. We've had people up on the ISS for months at a time, and been able to study that, but we've never landed anyone on Mars with its 38% of normal gravity, and the Apollo missions only spent a few days each on the Moon with its 16% gravity, and that was in between long zero gravity durations. So we have only educated guesses about how long you could live on either place before suffering health issues. I've spoken before many a time about using centrifugal force to simulate gravity, called spin gravity, or even combining it with local gravity where there isn't enough, so I don't want to spend too much time on it now. The short form is you take a big cylinder and spin it around, and the walls of that cylinder become the floor. Folks occasionally ask me if I'm oversimplifying how easy or functional this is, and assume that if it were that easy and effective, we'd do it on the ISS. There's a flaw in that reasoning. The main purpose of the ISS is scientific, and the major feature it offers us that we can't do down here on Earth way cheaper is a lack of gravity, so putting it on the ISS would be counterproductive, especially since one of those things we study up there is health effects of zero gravity on people. But spin gravity offers us some problems. The one we most often consider on this channel, because we mostly contemplate huge structures, is that spinning something around places it under a lot of force, equivalent to what a suspension bridge of equal length to the cylinder's circumference would experience on Earth. On the other side of that size issue, if you go too small, then you have folks experiencing a significantly different force on their feet than their head. On Earth, gravity is just a bit weaker on your feet than your head when standing up, but the difference is so small only our finest instruments could detect it. Standing on the walls of a cylinder 5 meters in radius, if gravity is normal at the ground, it's about 40% lower at your head. We can assume that would be pretty nauseating. In case it isn't, the whole thing is spinning around at 13 RPM, about once every 4 seconds, which will probably succeed in nauseating you if the difference in gravity did not. That's faster than the typical tilt-a-whirl they have at amusement parks and festivals. From our experience with such things, and more scientific if less fun versions, We know people can handle about 2 RPM, one rotation every 30 seconds, without feeling nauseous, and that most people should be able to adapt to a bit more. Unfortunately, to achieve 1 gravity at 2 RPM means your cylinder needs a radius of 224 meters, which is a circumference of 1400 meters. Plenty of living space, but bigger than we normally envision space stations or ships, though on this channel we routinely discuss ones that would have closets bigger than that. However, centrifugal force goes with the square of those RPMs, and linear with the radius. So if we want to simulate Mars or the Moon's gravity, 38% and 16% of Earth's, the necessary radius of our cylinder would drop to 38% or 16% respectively, or 85 and 36 meters. Alternatively, if we up the RPMs from 2 to 4, our radius for normal gravity would drop to just a quarter, 55 meters. Kick it up to 6 RPM, which we've decent reason to believe most folks could adapt to after a while, and it drops to just 25 meters radius. It's also possible half gravity is fine, maybe even less. Again, we have 0 experimental data on how much gravity is okay, just that none is not. If you wanted to simulate Martian gravity on a ship on the way there to get everyone used to it, and you found they could handle 6 RPM, then a 10-meter diameter is all you need. It also doesn't have to be a cylinder or even a ring. Spin 2 pods attached by a beam or a tether, and they could have spin gravity in the pods. You do have to worry about wobble on such things, but it's not too huge an issue. We can use counter-spinning sections, gyros, and so forth. Now, as I said, and have spoken of in some other episodes, you can slope a floor using a bowl shape and spin that to combine local gravity and spin gravity. Often when I've spoken of this, since it's usually been in passing, I've implied it's a fairly shallow bowl, but in practice it would be more like a buried cylinder with a slight curve, adjusting its angle with the weakening spin gravity to keep down pointed at the wall. On Mars it would be a deep bowl. On the Moon it would be more like a very deep vase. You do not have to bury it underground, but it is a good way to protect from micrometeors, and the view is never good from inside a rotating habitat smaller than planet-sized, since your windows would be in the floor and the stars would spin around a couple times a minute. Excavation is also very easy in low gravity, and you can pile tons of material on top of something that isn't all that structurally strong. We discussed this concept more in the rotating habitats episode, but it is worth noting that windows would be on the floor and wouldn't make for a good view, since you are spinning around a couple times a minute or more, so you probably wouldn't have a lot of windows. This brings up lighting and temperature, our next 2 topics. So far, our energy needs have stayed pretty mild, well under the normal electrical use of the typical citizen of an industrialized nation. However, when it comes to keeping things warm and bright, your energy bill can shoot up quickly. Just doing lighting for one person to see by is cheap enough. Modern LED lights are durable and low powered, and even a 10-watt bulb provides comfortable lighting. But when we start talking about lighting up large sections of hydroponics, that changes. We've discussed that in the past a few times too, and I usually place 2000 watts as the bare minimum energy supply for lighting enough plants to feed a person, and I tend to assume everything has been optimized. Not just lighting done only in those wavelengths and luminosities needed by those plants, but also temperature, humidity, CO2, etc. Of course, the sun provides free sunlight, but using that isn't always a good idea even when it is an option. Temperature though turns out not to be as bad as you might expect if you live in a cold climate, are used to an expensive winter heating bill, and are thinking space is freezing cold. In space, heat can only escape or enter an object by radiation, shining light on it, or the infrared radiation emits based on its temperature. That's the effect of vacuum, and even on the Moon a lot of those things would be clad in a vacuum, same as any vacuum flask, the thermos being the best known of these. But these are not insulated just by a vacuum cutting off convection and conduction. That wouldn't keep something warm for long. Rather, the inside of the outer layer is made to reflect infrared light back into the inner vessel, cutting off even that means of emitting energy. This is something we usually bypass mentioning in most of the space-based constructs we discuss on this channel, because we are typically trying to get rid of heat as fast as possible, since we tend to be generating tons of it. But when you're not, that inner layer helps a lot, because even if you are only emitting heat by radiating it, not via conduction or convection, you can radiate it away pretty quickly. Heat radiation is entirely based on how hot the object is, and how much surface area it has. and a man in a spacesuit has about 2 square meters of surface area and is radiating about 500 watts per square meter at human body temperatures. That's 1000 watts you are emitting by default, the equivalent to burning 21,000 calories a day, so anything you can do to cut that down in terms of insulation is a good idea. Of course, in a spacesuit near Earth or on the moon, when you are exposed to sunlight, you can overheat very quickly instead, particularly if you're wearing black instead of a nice reflective white. The same applies to domes or habitats. Properly insulated, they don't need much heating, especially if sunlight is coming in and you have a ton of thermal mass available, which you would on the moon or Mars if you don't mind digging down a ways where the temperature won't fluctuate as much. Day length is about the same on Mars as on Earth, but the moon's day is a month long, and you really need to factor that into considerations for staying cool in the day and warm in the night, and burying yourself helps with that, and with protection from meteors and radiation too. That's one reason why artificial light, or light bounced in through mirror and lens assemblies, is better than the classic glass dome. We talked about that more in moon-based concepts. Mirrors and parabolic dishes, especially ones that are just polished metal, are cheaper and harder to damage than a glass dome, so you stick them around the thing you want lit and let the light come in through windows instead. You can also use that reflective surface to filter out any frequencies you don't want, or want less of, like infrared or ultraviolet, or even green if you have hydroponic areas you have to worry about overheating, since green light does little for plants. The other nice thing about the moon as opposed to a space station is that we do have the option of cooling with conduction or convection, as well as warming. All that lunar regolith around and below you can be used to dump waste heat, or to help warm the installation during the night. It's a lot easier to dig pipes for that purpose there too, again from lower gravity. So lighting and temperature can be pretty cheap, or very energy expensive, depending on the circumstances. We've got 3 more things I want to touch on briefly before we close out: construction, communication, and manufacturing. Communication is another one of those no-brainers, but it certainly helps to have a stockpile of information on site in case they go down. Manuals are not the same as having a crack team of experts on any field available to help on short notice though. It's also your sanity lifeline home, so you can talk to friends and family, but again this needs little detailing and is a no-brainer. It becomes a much bigger issue as you get further from Earth and time lags of minutes or even hours can come into play, and also require transmitters that use significant amounts of power. As to construction and manufacturing, the biggest cost and hurdle to doing a moon base or giant space station is the cost of getting material and equipment there. Anything you can manufacture on site or in situ saves tons of money, and of course anything you need to live is ideally something you should be able to make on site. In space you need to bring all your material, so most of the time it makes more sense to make the stuff here and ship it up to space. But even there, some manufacturing ability is very useful, and you can save a lot of mass if you don't need 50 spare parts and a lot of specialty tools because you can 3D print them on the spot if they're needed, and maybe even recycle that mass when they're done. But simple 3D printing, and even the ability to make construction material for buildings out of local regolith, isn't really enough. Taking that hydroponics example for instance, you need to be able to make machines to bake you air out of and to smelt that regolith to make steel or aluminum and glass and solar panels and wiring. You need to be able to make trays and piping for the plants either out of metal or plastic, and if the latter, you probably need vats of algae to make your plastics and so on. Needless to say, anything which can miniaturize or automate manufacturing with that degree of intricacy helps us out enormously. I think that is where we will stop for today. We could do, and probably will do, whole episodes going into more in-depth looks just at in-situ resource exploitation, but that would take at least an episode, and is probably better discussed in terms of each place we would do that at, as the options are different for Venus and Mars and Titan and so on. There's a number of books that have been written over the years about surviving on the moon. My friend Bob Goddard wrote one titled Mother Moon not long back, and it begins right where we started, with a lunar colony struggling for survival when supplies stop coming from Earth, though it ends in a very different place. I won't spoil the plot for you, but until next time, thanks for watching, and have a great week.